Welcome to UV Physics Academy. So here we are discussing the solutions of quantum computation. This is the first question. They are asking to show that these vectors are linearly dependent. For example, let us suppose n is the number of vectors given and m is the dimension of the vector space or Hilbert space. Then here we have three conditions. Sometimes maybe n is greater than m, or sometimes n equal to m, or sometimes n less than m. Whenever the number of vectors given is greater than the dimension of the Hilbert space, we can say that these vectors are linearly dependent. But whenever these two cases, we cannot say directly. So here we have to find the determinant. We have to find the determinant of the matrix formed by the vectors given as a columns. And once you find the determinant, here you will be having again two cases. Sometimes maybe determinant is equal to 0, or sometimes maybe a determinant is not equal to 0. If a determinant is equal to 0, we can say these are linearly dependent, and not equal to 0, linearly not dependent, and we can say linearly independent. Okay, so according to this concept, here three vectors are given, but the dimension is 2, so that's why we can say these vectors are linearly dependent. So let us try in another way also. Now for example, if we take this coordinate system x and y, and I am going to represent these vectors. So here it is origin O, and here it is let us say 1, and this is a 2, and this is a plus 1, and here it is a 2, and here this is a negative axis, that's why this is a minus 1. Okay, so now the first vector 1 comma minus 1, this is the vector 1, and second vector is 1 comma 2, so this is the second vector 1 comma 2, and this is a 2 comma 1, which is a third vector. If you see carefully, the first vector is in the span of these v2 and v3. That means v2 and v3, sorry, v1 is spanned by v2 and v3. So we can write like this: v1 is spanned by v2 and v3. So what is the meaning of this? Let us suppose there is a real space, 3 dimension. What are the unit vectors? I cap, j cap, k cap. Of course these are the basis states. What is the meaning of that? If you want to write any vector, you have to write as a linear combination of I cap, j cap, k cap in 3 dimension. So that means that a 3D real space is spanned by I cap, j cap, k cap. So if you want to write any 3D vector, you have to write it as a linear combination of I, j, k. Similarly, whenever v1 is spanned by v2, v3, we can write this v1 as the linear combination of v2 and v3. Okay, so for example, if you take this v2 1 2, and here it is a 2 1. If I take minus here and plus here, I will get here it is 1 and minus 1. That's it. So these are the three cases. N greater than m, always linearly dependent. N equal to m or n less than m, we have to find the determinant. But you may get doubt. Whenever n less than m, we can't write it as a square matrix. Determinant exists only for square matrix. No need to worry. So that means you are having one column short. That's why you can take that one column as all ones 1 1 1 and find the determinant, and same rule. If determinant equal to 0, linearly dependent, determinant is not equal to 0, linearly independent. So this is our next question. So here they defined one linear operator A like this. A operates on ket 0 computational basis 1, and A operates on 1, we got ket 0. First they are asking the matrix representation of A, but see here they are asking first one, input basis and output basis are same. That means we have to take a computational basis as input and output basis. Okay, so here I am taking this operator representation by taking input basis 0, 1 and output basis also ket 0, ket 1. Okay, and how to represent this in the matrix form? Just take this way. This is the operator A. Here always we have to take a input basis, and here we have to take a output basis. Now input basis ket 0 and ket 1, output basis ket bra 0 and bra 1. Some people are writing here ket 0, ket 1, but I think this is the better representation. Now A operates on 0, what we are getting 1. So whatever you are getting, that will be making inner product with this output basis. If you make the inner product with this output basis, here you will get 0, here you will get 1, because 1, 1, this inner product bra 1 and ket 1 inner product is equal to 1. Similarly, if A operates on 1, what we are getting 0. Whatever you got, just take it and make the inner product with output basis, that is 0 into 0, that is 1, and here it is 1 and it is a 0, it's a different, that's why it is a 0. So finally we got this matrix representation 0, 1, 1, 0. And here in the second part, what he is asking to represent A by taking a different basis. Okay, so let us take like this. Now here I am taking input basis as 0 and 1, which are computational basis, and output basis I am taking as a diagonal basis, plus, minus. So you know what are these diagonal bases? Plus is equal to 1 by root 2 ket 0 plus ket 1, and this minus, which is a linear combination of a computational basis 0 minus 1. Okay, now let us represent this operator in the matrix form. I told you already, here you have to take input basis, which are 0 and 1 in our case, and here we have to take output basis, which are diagonal basis, like this. Now how to write this element? This is A11, first row, first column. So here A11 equal to first row plus operator, first column 0. That means A operates on 0. If A operates on 0 already defined, we got 1. So this is the inner product of plus and 1. If you make the inner product of plus and 1, what you will get here? This coefficient. How much? 1 over root 2. And similarly, if you find A12, again first row, second column. So plus operator, second column 1. So A operates on 1, we got 0. So this is nothing but inner product plus and 0. If you take this inner product, this plus and 0, here you will get this coefficient, which is equal to 1 by root 2. So here I have done this 1 by root 2 and 1 by root 2. So I request you please do this yourself, this and this. This is nothing but A21. So second row, first column minus A ket 0, just operate, and here you will get minus 1 by root 2, and here you will get 1 by root 2. So I request you please do this yourself. Then we got the matrix representation of A, but remember we have changed the output basis as a plus and minus. So this is 1 over root 2, 1, 1, minus 1, 1. So if you want further more exercise, you can change the input basis as a diagonal basis and output basis as a computational basis. Or Input and output basis both are diagonal basis. You can try yourself, and if you have any doubt, please contact. The third question. So in this question they have defined two operators A and B. A transforms V to W and B is a linear transformation from W to X. What they are asking is the combined linear transformation BA is equal to the matrix product of B and A with appropriate basis, something like that. Okay, so let me take one example and explain this concept. So before going to do the mathematics, let me take one example. So as usual, A is a transformation from V to W. That's why my input bases are V and output basis Wj. So let us represent this matrix, this operator in the matrix form. Let us define the vector space for 2 dimension. That's why V1 and V2 for easy. This is a W1 and a W2. So what is this element? First row, first column, first row, second column, second row, first column, second row, second column. Now let us define what is this operation. If A operates on V1, what is the meaning of this? If A operates on V1, just see this column. A11 W1 plus A21 W2. Later, whenever we are doing this quantum circuits also, this notation is very useful. Please learn here. So A operates on V2. So see this is a second column. A12 W1 plus A22 W2. Now let us take B operator. So the B operator is the transformation from W to X. So here the basis states are already given. So this is from Wj to Xk. Okay. So now let us represent this B matrix. That means a B operator in the matrix form. Here input basis I am taking W1 and W2 and output basis X1 and X2. Okay. So this is the first row, first column as usual. This is a B12 and this is a B21 and this is a B22. So what is the meaning of this? Say here if a B operates on W1, we will get the linear combination of output basis X1 and X2, which is B11 X1 plus B21 X2. And similarly, if a B operates on W2, we'll get the linear combination of X1 and X2, which is B12 X1 plus B22 X2. Okay, so now let us take the combined operation and let us prove what he is asking. Okay, now I am taking this combined operation. So so let us take the combined operation. This is a BA. So here first you have to come from right to left. That's why first operation is A and the next operation is B. So A transform V to W and B transform W to X. So finally here our input bases are Vi and output bases are Xk for the combined operation BA. Okay, so let us take BA operates on this one. So V1 I have taken. So now this A operates on V1 first. Already we know what is A operates on V1. Please take this linear combination. A11, see this one, W1 plus A21 W2. Nice. But this B operator is as usual. Now this B operator is operating on W1 as well as W2. So first let us take this W1. Now the B operates on W1, we are getting B11, a linear combination of X1, X2. But remember, we can't interchange these two. The reason is we don't know whether these two operators AB are commuting or not. If they commute with each other, we can write AB equal to BA something. So that's why we don't know here whether they are commute or not. So let it be like this only. Don't interchange the places. Now B operates on W. You have a linear combination. First place is B only, B11, and give the space for that A11. And as usual X1 plus again first place is a B21 and the second place keep that for A11 X2. So plus again this is B operating on W2. So this is the linear combination. Just take it and write. But keep this second place for A21. So that's why this is B12, A21, X1 plus B22, A21, X2. That's it. Okay, so if you see carefully, here it is X1 and here it is X1. If I take common, so B11, A11 plus B12, A21, this is X1 plus similarly B21, A11 plus B22, A22 and this is a ket X2. Now if you observe carefully, so what is this? This is the first element of a BA. Whenever this matrix B is multiplied with A, you will get this row and column B11, A11 plus B12, A21. And similarly this one is again the same thing. Okay, so here we can write like this also. If you observe carefully, if you cancel this 1 1 row and column, row and column, so you got 1 1 1 1. So this is nothing but the BA matrix combined matrix product. First row, first column, X1 plus, and here also if you see this row and column gets cancelled, and I think this is not 2 2. I'm sorry. So this is not a 2 2. This is a 2 1. This is a 2 1. So here also 2 2 gets cancelled, and you got this the element. Which element it is? Second row, first column. So this is nothing but a BA second row, first column X2. So BA operates on V1. We got this. So similarly, I request you, please try this yourself. BA operates on V2. So you can guess what you are going to get. So that's a linear combination of X1 and X2 only. Okay, and after that, this is first row, second column. So that's why this is a BA first row, second column. Okay, combined product. Please, I request you, please do this algebra, then you will understand. And this is as usual a BA a 2 2. So if you want to write this matrix form, so this is a BA combined operation, and the input bases are V1 and V2, and output bases X1 and X2. And see this one, BA operates on V1. We got a linear combination of X1, X2. This is a BA first row, first column. I'm sorry, this is a combined matrix BA11, and this is a BA 2 1. And similarly here BA 1 2, and this is a BA 2 2. So this is by using an example we can show that the combined operation BA is nothing but the matrix product of BA. Okay, so let us do now the mathematics. Okay, now let us do the mathematics here. So as usual, I am taking this operator A, which is transforming this input basis Vi to Wg. So, and similarly, B operator is a linear transformation from which is a transforming Wj to Xk. So it's just like a change of basis. So if you want to make this a change of basis, if you want to do this changing the basis, we need to take this completeness rule. I'm using here the completeness rule. Let me explain what is this completeness rule. The sum of outer products of basis states is always equal to identity operator. That is summation over I. If I take my bases are psi I, outer product is always equal to I. So this is the completeness rule. The sum of outer products of all the basis states is always equal to I. Okay, now let us come back to the first one. So here we have Vi, these are the input bases, and these are transformed to Wj. Okay, first let us take a Vi. I think I can write this as IVI. Okay, I for identity operator. Now in the place of this identity operator, I'm using this completeness rule. To which basis I want to change? This one. So that's why I'm writing here summation over j. This basis I am taking Wj, and this is Vi. If you observe carefully, this is nothing but a inner product, which is a scalar. So we got inner product, that means summation over j as usual. We got the inner product Wj Vi, and here we got Wj cat. So what is this? This A is a transforming Vi as a linear combination of Wj, because this is a constant. In our earlier example also we have seen here, if you observe carefully this one. This A is operating on V1, we got the linear combination of W1, W2. So this is also same. So we can write like this. This A operator operates on Vi. We are getting is a linear combination of Wj. And what about this? This is the matrix element. This inner product, whatever you written here, that is the matrix element. So what is that matrix element? This is the matrix element corresponding to A, which is equal to A. This is the row and this is the column. Bra vector row and ket vector column. So that's why this is AJI. So finally we can say A operates on Vi is equal to this is summation over J, AJI, Wj. Now you got the clarity. Please check this one, these two examples. Okay, so here this is the result of, this is the mathematical form, and here this is the example. Now similarly go with the B. If you're still not understanding, let us take a B. So here input bases are Wj, and which are transformed by B to Xk. So that's why first I'm taking this Wj, and I think I can write this as identity operator, no issue. And now this identity operator is, we are writing in the outer product, this complete by using this completeness rule. So I'm going to write this in the form of this basis, that is summation over k, outer product, xk, Wj. Now again this is nothing but, this is a constant. We can write like this, summation over k, xk, Wj, and this is ket xk. Again we got, so this Wj and operated by this B. So B operate on Wj, we got some constant, inner product constant. It's a linear combination of output basis. It's a linear combination of output basis. So I think we can write this as a matrix element. Similar to that, this is the matrix element B. This is the row and this is the column. Always a bra vector take it as a row and a ket vector take it as a column, Kj. So we can write this as B operates on Wj, will get summation over k bkj and ket vector xk. So if you observe the earlier example, this one. So here what we get, the B operates on Wj, we got the linear combination of xk, the same. W1 linear combination of x1 x2, W2 linear combination of x1 x2. Fine. So now let us take the combined operation of this BA. So I'm going to take the combined operation of BA. So here the combined operation of BA. So what is this? First Vi is transformed to Wj, and again this is a transformer to xk. Here I am writing, there is no space. Here Vi to Wj and Wj to xk. Right. So now we have to take the combined transformation BA now. Let us see. Right. So now let me write again. So here we are talking about the combined operation BA. So what is this combined operation BA? So here we have the transformation Vi to Wj and Wj to xk. So this will be done by A and this is B. Okay. So now I'm taking this B, A. The first one is a Vi. So this is nothing but, so operate A on Vi. Already we have this one. So A operates on Vi. We got summation over J, A, Ji, Wj. So don't change the place of this B as it is. And this is a summation over J, A, Ji, and this is a Wj, linear combination of W. Now, so next B is operating on Wj. So that is also we have already we represented by using this completeness rule. Now take this and substitute there. But remember, don't change the order of that B and A. So which is, so keep that A, J, I as it is. Now here B is going to operate on Wj. So that is summation over K, and that summation I am writing outside here. And this is a bkj, and that AJI, please don't interchange that positions, and this is xk. That's it. Now if you observe carefully, this is kth row jth column, this is the jth row ith column, this jj gets cancelled, and we can write this as combined of matrix product BA, matrix product BA, kth row and ith column. So this is xk as usual, and this is the already j cancelled, that's why this is a summation over k, and this is nothing but the combined operation BA operates on Vi. So here this represent the combined operation of BA as a matrix product. If you see our example, our example earlier, this one, linear combination of x1 x2, and here also the same thing. Okay, so that's it, and this is the I have explained this by using an example and as well as by using this completeness rule. I hope you understand. If any doubt is there, please contact. Thank you. So here this is the fourth question. So they are asking to show that identity operator is having all the diagonal elements 1 and the rest of the elements are 0. Okay, so first let us take example, and after that we will do that mathematics. So here I'm taking so basis states, 3 basis states I am taking. So V1, V2 and V3 are the 3 basis states. Now if you take identity operator, operates on V1, we'll get V1. So this can be written as 1 V1 plus 0 V2 plus 0 V3. And similarly, if I identity operator operates on V2, we'll get V2 only, same state. This can be written as 0 V1 plus 1 V2 and plus 0 V3. If you take that V3 similarly, this identity operator operates on V3, we'll get V3 only. And this can be written as 0 V1 plus 0 V2 plus 1 into V3. So if you write this in the matrix representation, so this is the identity operator, and here we have input bases V1, V2 and V3, and here we have output bases V1, V2 and V3. So here input and output bases both are same. Now see, if I operates on V1, we got a linear combination of this V1, V2, V3. So here is a 1 V1, this is a V1, that's why it's 1, and a 0 V2, and this is also 0. And here the same, a 0, this is a 1 V2, here 1, and this is 0. So 0, 0, and here it is 1. So we can show this by using one example like this. Let us do some mathematics now. So by using completeness rule. Okay, so here I'm going to use this completeness rule. So here I'm taking the input basis Vi. So under this transformation identity, that means identity operator is operating on this. So I think we can write this as I Vi. So now I'm using this completeness rule and replacing this identity operator like this. Summation over j. This is the outer product Vj like this. Now just take it and substitute. Now summation over j. This is a Vj outer product into Vi. Now this is nothing but identity operator operates on Vi. So if you carefully observe, this is nothing but the inner product. So which is a scalar. So here we have written, we can write summation over j, the inner product Vj, Vi, and this is a ket Vj. And this inner product is nothing but a Kronecker delta function, which is a delta Ij. So now this is the summation over j, delta Ij, ket Vj. So what is the meaning of this? So whenever identity operator operates on this Vi, we got this. So Kronecker delta. So this value equal to 1 if I is equal to j and 0 if I is not equal to j. What is the meaning of I equal to j? Diagonal elements. So here this I equal to j is nothing but diagonal elements. And this I is not equal to j means of diagonal elements. So all diagonal elements are equal to 1 and all of diagonal elements are equal to 0. Like this we can do by using this completeness rule. So here this is the next question. So they are asking verify this is an inner product. So here what is this notation? So actually let me introduce first Dirac notations. Okay, so here I'm introducing this Dirac notations. After that we will discuss this problem. So whenever you have a state vector in the Hilbert space, this is represented by ket psi, and the corresponding complex conjugate, that is a psi star, is represented by a bra vector. State vector is represented by ket vector and its corresponding complex conjugate is represented by bra vector. Now whenever there is a constant in ket vector, that constant will be out as it is. Okay, and whenever the constant in ket bra vector, So you will get a complex conjugate of that A into bra vector. Constant you can write anywhere, here or here, does not matter. Whenever an operator is there inside the ket vector, so this will be out as it is. And whenever an operator is there in the bra vector, so here you must be very careful. So you can't write this operator A out this in this here. So you have to write like this. This is the psi. Whenever an operator in the bra vector, you will get the Hermitian conjugate or complex conjugate, that is A dagger. But you should not write here. You have to write beside this vertical line only. So these are the these are basic Dirac notations. Now let's come back. So what is this notation? So here in the textbook, they are using this notation. So what is the meaning of this? So here one state vector, here one state vector, that is a psi comma phi. So this indicates the inner product. So in a Dirac notation, we can write this as a bra and a ket, bra psi and ket phi. So now this inner product is having a few things to verify. That is, this is a linear in the second argument and conjugate linear in the first argument. So, and the next one is a norm is always positive. So these are the three conditions we have to verify. So once again, first one is linear in the second argument. And the second one, here we have to show this a complex conjugate. For example, we have phi psi, it's a complex conjugate is nothing but psi phi. And the third one, the norm is always greater than or equal to 0. And another one is conjugate linear in the first argument. That is the next question actually. So we will discuss here. Right. Okay. So let us prove these things. Now, first one, this inner product is linear in the second argument. Second argument. What is the meaning of this? So this means, now for example, I'm taking this psi comma phi inner product. I'm talking about this second argument. So this is nothing but psi as it is. And the second one I am writing as a linear combination, a summation over I, lambda I, phi I. And I have already given this notation. Whenever there is a constant in the ket vector, it will be out as it is. Summation over I, lambda I, this is psi phi I. Okay, so which can be written as in this format. So this is nothing but lambda 1 psi phi 1 plus lambda 2 psi phi 2 and so on. So this is the meaning. Linear in the second argument. Okay, and the second one. So here, if you take the complex conjugate, these are two states are interchanged. Let us see this one. Now here, I'm taking first a phi comma psi inner product. According to this Dirac notation, I can write this as phi and psi. Now for this, I'm taking complex conjugate. I'm taking this complex conjugate, that is phi comma psi, the complex conjugate, which is nothing but phi psi complex conjugate. Here I have already defined ket vector complex conjugate. That means in the Dirac notation, if you take a ket and apply conjugate, you will get a bra and vice versa. So once you apply the complex conjugate, this bra vector will become ket vector and this ket vector will become bra vector. So this is a psi and a phi. So which we can write this as psi comma phi with this notation. So second one is also proved. And third one, so this is the norm. Norm is nothing but length of the vector in higher dimension. So let us take this psi comma psi, which is nothing but bra psi and ket psi. So this is the bra vector and ket vector. We can write this as a psi star into psi. So use this notation, which is nothing but mod psi square. Whether psi may be real or complex, but once you take the mod square, this is always positive. This is always positive. So here we have discussed the three properties of this inner product, and the next one we will discuss this as another property. So here they are asking, show that inner product is a conjugate linear in the first argument. Okay, so let us take this inner product. So here I am taking a psi comma phi. So I'm using the Dirac notation for this. Okay, so this is the psi and phi. I'm talking about this first argument here. So this is summation over I lambda I psi I, which is a linear combination of basis states, and this is a phi. Okay, so we have already discussed earlier, if any constant is there in the bra vector, you will get its corresponding complex conjugate. So here, so this is nothing but the summation over I. This lambda I is in the bra vector, so lambda I star, this bra psi I phi. So this is nothing but lambda 1 psi 1 phi plus lambda 2 lambda 2 star, I'm sorry, lambda 1 star phi plus so on. So if you want to write this notation given in the textbook, psi comma phi equal to lambda 1 star psi 1 comma phi plus lambda 2 star psi 2 comma phi plus lambda 3 star psi 3 comma phi plus so on, like this. So finally, inner product properties, it is a linear in the second argument and a conjugate linear in the first argument, and whose whose norm is always positive, and it satisfies this complex conjugate rule. Right. So here this is the next question, and this question is related to orthonormalizer condition. First, let us discuss what is this orthonormalizer condition. Orthonormalized condition. Right. So for example, we have two state vectors. Let us say psi I, psi j. This is nothing but delta ij, which is a Kronecker delta function. So this value equal to 1 if I is equal to j, and 0 if I is not equal to j. So that means this one condition is called normalized. That means these two are same, and if it is equal to 1, that state is said to be normalized state, and a 0, this is a orthogonal condition. So this is the orthogonal condition and this is the normalized condition. Okay, so first let us check whether these are orthogonal or not. Here they have given, so W equal to 1 1. I'm writing the ket vector notation. See, ket vector, you have to write it as a column matrix, and the bra vector, you have to write it as a row matrix, but you have to take complex conjugates of the elements. I repeat, ket vector column matrix as it is, but bra vector, you have to take a complex conjugate and write it as a row matrix. But of course, here we have all real elements only. V equal to this is a 1 minus 1. So let me check whether these two are orthogonal or not. Now I am taking the inner product of W and V. These two states are different. So if I get 0, those are orthogonal. Let us check. So this is the bra vector. So I have to write it as a row matrix and no complex conjugate because these are real. And here this is the ket vector, which is a column matrix. So if I multiply here, I will get 0. So this is, I mean, these two states are orthogonal. And after that, they are asking what is a normalized form of these two states. They are not normalized because if you take the dot product here, you won't get it 1. That means, sorry, inner product of W, if you take, you won't get 1. So how to get this normalization? For example, you have a state psi, which is AB, and its normalization constant is given by, the normalization constant is 1 over under root mod A square plus mod B square. We don't know whether A and B are real or imaginary, so that's why better to write this general form. So by using this, I can take a W, which is 1 minus 1. Its a normalization constant is 1 over under root 1 square plus 1 square. This is a 2. So the normalizer form is 1 over root 2, 1 minus 1. And here W similarly, which is, okay, I'm sorry. So this is a plus 1 and this is 1 minus 1. Okay, so normalization constant is again 1 over root 2 and this is 1 over root 2, 1 minus 1. That's it. Okay. Right. So if you have a doubt, so please contact. Okay. Right. So here, this is the next question. This is about Gram-Smith orthogonalization process. What is this Gram-Smith orthogonalization process? For example, they have given a set of linearly independent vectors. A set of linearly independent vectors. Okay, so we can call it as basis states. Now we want to convert this set of linearly independent vectors. That means this process will convert them into complete basis. Complete basis. What is the meaning of basis and complete? What is the difference between basis and complete basis? So here the basis, complete basis means they obey or satisfy orthonormal condition. Orthonormal condition. Okay, that means these basis states need not to satisfy this condition. So if you apply this process, whatever the basis states we are getting from this process, they definitely satisfy the orthonormal condition. That is, if you have the inner product psi I, psi j, if you make the inner product of two vectors, we'll get delta ij, canonical delta, which is equal to either 1 or 0. 1 if I equal to j, 0 if I is not equal to j. Earlier problems we have already discussed. 1 means normalization condition, that 0 is the orthogonal condition. Okay, so now let us suppose we have a set of vectors, let us say a v1 and v2 and v3. Let us suppose these are a given set of linearly independent vectors. These are basis states. So now we want to convert them into a complete basis. Let us suppose the corresponding complete basis states are E1 cap and E2 cap and E3 cap, so on. So let us discuss how to construct. So for the first one, E1, you have to take this first vector as it is. That means let us suppose U1 equal to V1. First I will get U1 and from this I will write the corresponding unit vector, that is simply a vector by its magnitude. So we can write this as U1 by its a normalization constant, which is nothing but norm, or we can write it as inner product. Right. So we got the first vector, this one. This is very easy. And next, if you want to get the second one, so here onwards the process starts. Listen carefully. First one is a straightforward. Okay. Next. So here you have to find U2 next. How to get U2? So U2 equal to, it is defined as V2, the given vector, second vector, minus projection of V2 over U1. What is the meaning of this? So we have to find the projection of V2 over U1. For this, we have to take the projection operator corresponding to U1. What is the projection operator corresponding to U1? Already you got this unit vector. So just to take the projection operator, E1 cap, E2 cap. This is the projection operator corresponding to U1. So just take this and operate on V2, which is finally U2 equal to V2 minus, so one more time, projection of V2 over U1. That means take the projection operator corresponding to U1, E1 operates on V2. No need to get tension. Here you will get a scalar, and that scalar is multiplied with this E1, and you have to just subtract that from V2, second one. So as usual, I have to find the corresponding unit vector, that is E2 cap. Just I am finding the unit vector corresponding to U2, which is U2 by its magnitude or norm, or we can say this is a simply under root normalization constant, U2. Earlier we have given that is 1 by under root mod A square plus mod B square, which is nothing but the inner product of a psi, the inner product of U2. And similarly, second, if you want to find this E3, first I have to find the corresponding U3. So U3 equal to, this is V3 minus, see carefully here already we got two things, U1 and U2. So that's why projection of V3 over U1 minus projection of V3 over U2. So let us write this. So same concept. What is the meaning of a projection of V3 over U1? You just take the projection operator corresponding to U1 and operate on V3. So which is nothing but the projection operator corresponding to U1. This is outer product operates on V3 minus, this is the projection of V3 over U2. You just take the projection operator corresponding to U2, which is outer product E2 operates on V3. That's it. So once you got this U2, you can find the corresponding unit vector E3 equal to the vector by its magnitude or inner product or norm, whatever it is, U3 like this. So if you want to write more generally, so you can write like this also. Let me write here itself. Yeah, I will write here. So if you want to write more generally, so let us find U. This is so we have to find this UK from VK minus, here is a summation. If you observe carefully, for V3 we got two terms here. So summation, I'm taking some other dummy weight index J, I'm taking the outer product EJ. Okay, so it operates on VK. But if you observe carefully, whenever you are finding U3, you got only two terms here. One is corresponding to U1, another is the projection operator corresponding to U2. So you will get the projection operators, how many? Whenever you are finding U3, you got two projection operators. Whenever you are finding UK, this J is running from 1 to K minus 1. That's it. So this is once you got this UK, you can find the unit vector, corresponding unit vector uk by its magnitude. So this is the Gram-Smith orthogonalization process. Now let us consider one example for this and discuss. Okay. Now here I am taking one example to understand this method. So I have taken two vectors 3, 1 and 2, 2. If you see carefully, if you find the inner product of those two, it is not equal to 0. So it is not a complete basis. So how to make it a complete basis? Okay. So let us suppose this is our V1 and this is our V2. So first, as usual, I have to define U1, which is nothing but a V1, first vector as it is, no issue. So which is nothing but a 3, 1. So directly we can find the unit vector corresponding to this V1, which is V1 by its normalization constant, which is nothing but 1 by under root a square plus b square. Earlier problems I have already discussed. This is a 1 over under root 10 3, 1. So that is the even cap. Next, we have to find this E2. But before going to find that, first we have to find U2. U2 equal to this V2 minus projection of V2 over U1. So earlier we have already discussed this one. So what is the meaning of projection of V2 over U1? You just take the projection operator corresponding to U1 and operate on V2. So here what is the projection operator corresponding to this? V2 minus this projection operator E1, sorry. So E1 cap, this is the projection operator corresponding to this and which is operating on V2. And if you see carefully, here this is the inner product. Now let us find this V2, given V2 as it is, which is a 2, 2 minus, and here we have this inner product. Let us write this matrix form. This is the ket vector, so that's why E1 cap, which is a 1 over root 10. This is the ket vector as it is a column, and this is the bra vector, again 1 over root 10 whole square. And but this is a bra vector, that's why I have to write it as a row matrix. And this is a V2, the given one V2 as it is 2, 2. Now we just find this product. This is a row and a column, come from this side. So row and a column, 3 2s are 6 plus 2, that is 8. So we can write this as a 2, 2 minus, this is 1 by 10, and here we are getting this scalar. This scalar is nothing but 8. So this is 8 by 10 into 3, 1. You just subtract these two, and here you will get a minus 2 by 5 and a 6 by 5. So this is your U2. And from this, we have to find E2 cap. You just find this E2 cap yourself. And this E2 cap equal to U2 by under root this inner product. And I think this answer is equal to 1 over root 10. You'll get, I think 1 minus 3, or sorry, minus 1, 3. You just find it. Just take this same thing divided by this under root a square plus b square. Please do it yourself. And this is your final answer. Now you got E1 and E2 cap. So please check what is our result. So we got this complete basis like this: 1 over root 10, 3, 1, 1 over root 10, minus 1, 3. If you find this inner product of these two, you are getting 0. That is orthogonal. And if you take the self inner product, you will get 1. So which satisfies orthonormal condition. So this method is basically, if a set of linearly independent vectors is given, we can convert them into complete basis which satisfies orthonormal condition, right? So here if you have any doubt, please contact. Okay, right. Go to the next one. So here they are asking to represent the Pauli operators uh, in the outer product notation. Okay, so let us start. So let me take this identity operator first. This is 1001. Already basis states are given. If you observe carefully, this is the basis state. But how to write this outer product form? So whenever you want to write the outer product form, first write the matrix representation of this. So the matrix representation, I told you already. So here you have to take a input basis. Here our input and output basis are same. So this is ket 0, ket 1, and this is a bra 0 and bra 1. So my matrix is nothing but here 1 0 0 1. So if you want to write the outer product form, it's very simple. Wherever you have 1, so please round up those things. That means you will get only those terms corresponding to 1. Okay. So here I round up this one. Then I can write this identity operator in the outer product form. It's very simple. You just see this. Corresponding to 1, here you have bra vector 0 and ket vector 0. So outer product means ket into bra. I repeat, outer product means ket into bra. Okay. So just make this bra vector as a ket vector and this ket vector as a bra vector. And whatever the coefficient you have, non-zero coefficient, non-zero term, this is a non-zero. Whatever you have this coefficient, just take it and write here plus. Of course, these terms won't get, so because of zeros. And here we have 1. Okay. So again, this is nothing but make this bra vector as a ket vector and make this ket vector as a bra vector. Now let us go to this Pauli matrices. This is x 0 1 1 0. So first let me write this matrix representation. Ket 0, ket 1, bra 0, bra 1. So 0 1 1 0. You need not to bother about that 0 elements, leave it. Only just round up this 1 and this 1. Now see this one. So the Pauli X matrix X is equal to, here this is the 1 corresponding to this one. Here is the bra vector, make it a ket vector. Of course, this coefficient whatever you have, it will come here. And this is the corresponding ket vector, make it a bra vector. That's it. Plus, and here is a 1. Make this, coefficient is 1. Make this a bra as a ket. And the corresponding, make this a ket as a bra. So similarly, you can go with the y. This is a 0 minus iota and a 0. So first let us write this matrix representation. Y, ket 0, ket 1, bra 0, bra 1. So this is 0 minus iota, iota 0. So wherever non-zero is there, just round up. So here, this is a y equal to the first element, non-zero element, minus iota. The corresponding to this is the bra vector and this is the ket vector. So just convert this bra as a ket and write this ket as a bra. Plus next non-zero element, iota, and make this bra as a ket and the corresponding ket, make it as a bra. That's it. So if you take this z, so similarly you please try this. Z is equal to this 1 0 0 minus 1. I request you please try this. You will get this in the outer product form. Here is a 1, here is a minus 1. So you'll get a minus 1 1 because it's a diagonal matrix. You please try this. And this is one way of writing operators in outer product form. Let us try in another way also. Whenever you have some operator, any operator can be written as a outer product form. That means a linear combination of outer products, linear combination of outer products of base states. Okay, so how can we write this? For example, you have this Pauli X matrix I am taking. So if X operates on 0, we are getting this 1, and X operates on 1, we get 0. So based on this operation, we can write the outer product form. So what is that outer product form? This outer product form is given by always a summation over I, always this is the initial state and this is the final state. So what, I'm sorry, I think, yeah, this is, here this is a psi initial and this is the psi final. This is the outer product form. If you observe carefully, X is equal to, now this is the initial state 0 and finally we got 1. So that's why we can write it as ket 0 bra 1 plus initial state 1 and final state 0. And similarly, if you take this y, that means y operates on 0, what you will get, we'll get iota 1, and y operates on 1, you will get minus iota 0. Let us check the outer product form. The outer product form is equal to simply summation over I. Remember, psi initial is in the ket and psi final is in the bra vector. Okay, so careful. So now y is equal to, so what is the initial state here? Ket 0. What is the final state? Careful, you have to take this iota also, iota 1. But whenever there is a complex, there is a constant in the bra vector, you will get the complex conjugate. So that's why this is a minus iota, I'm sorry, let me finish it, plus next, what is this input here, sorry, initial state here 1 and final state minus iota 0. You have to take this constant also, and we know already whenever there is a constant inside the bra vector, you will get a complex conjugate minus iota 0 1, and whenever there is a constant, say it will, you will get a complex conjugate which is iota. So let us compare this with the earlier one. So minus iota 0 1 outer product plus iota 1 0 outer product. Yeah, same thing. And third one, I request you please try. So whenever Z operates on 0, this is based on the operations, and Z operates on 1, we'll get just a small phase change, that is pi phase change minus 1. So I hope you please try this and you will get this same thing. That's it. So initial, final, initial and final, there is a minus sign, that's why you will get minus. So any operator, we can write this as a outer product form by using this technique, which is a summation over I outer product, but that outer product ket psi initial and bra psi final. Please remember, initial state is in the ket and final state is in the bra vector, right? Right. So here this is the next question, and here they are asking this outer product Vj in the basis of, we want to represent this in the basis of yeah. Remember one thing, whenever you are changing the basis, always use a completeness rule. Okay, so one more time, completeness rule, completeness rule. So here they have given, they want to change into this basis, that's why we can write the completeness rule, this I equal to summation over I, this outer product, the sum of all outer products of the basis states is always equal to this identity operator. Okay, now let's come back to our problem. So here they have given this outer product operator, that is Vj, Vj. Okay, so now we can write this as I Vj, right. Now I'm going to replace this I with this completeness rule, which is summation over I. This is the outer product Vi, and the rest of the things as it is. Just write this as it is. Don't get tension, as it is. Now if you observe carefully, so here we have one inner product. So in the earlier problems also we discussed this inner product is nothing but Kronecker delta, delta Ij. So we can write this as summation over I, and this is delta Ij. Okay, and here we have again one more outer product we got. This is a Vi, careful, and the rest of this the remaining thing is a Vj. So here we have written this Vj outer product in this form. So what is the meaning of this? So finally one more time I'm writing here. So Vj equal to, I got this summation over j, sorry, summation over I, delta Ij, and this outer product Vi Vj. Okay. So you know this property of Kronecker delta, this is equal to 1 only when I equal to j, that is a diagonal, and 0 if I is not equal to j. Okay, so if I take this matrix representation like this, now let us suppose this is the outer product, given outer product, and here I am taking the basis states input. So ket vectors v1, v2, and v3, so on, so on. Let us say somewhere vj or vi, anything you can take. It's not a problem. So vi or vj, because only I equal to j, then only it is 1. So here bra vector v1 and v2 and so on. Okay, v3 and so on. This is a vj. So where you will get 1? Oh, sorry, not along the diagonals. Where you will get this 1 minute. Right, okay. So this means what? Here we will get only one element and the rest of the elements are 0. So we remain with either Vi outer product or Vj, anything, because all the terms will be 0 except this I equal to j. So that's why just I am taking this Vj here. So only this term remains and the rest of the terms are 0. So here Vj and here Vj. So only this one is a 1 and the rest of the elements are a 0. So that's it. So if you want some more clarity, so this is having a best example. So here for example, if you want to write this 0 0, which is nothing but 1 0 0 0. This is the matrix representation. So only the element corresponding to ket 0 and bra 0 is 1, rest of the elements are 0. And similarly, if you take this outer product 1 1, so this is 0 0 0 1. So here the only this element corresponding to ket 1 and bra 1. So if you have any confusion here, so please see this example, you will get clarity. So only that element is 1 and the rest of the elements are 0. Okay, so that's it. And if you have any doubt, so please contact. Thank you.